Hello everyone, myself Sarananda Gowda. Today I am going to explain the topic deep learning. In the deep learning, that topic is an improved deep reinforcement learning algorithm for path planning in unmanned driving. Agenda Introduction to autonomous driving and um, path planning methods, deep reinforcement learning, DRL overview, proposed DRL-PP algorithm structure and components, experimental setup, simulation result, reward and training performance, conclusion and further directions. Introduction to the topic, focus and autonomous driving. The presentation addressed challenges in autonomous driving, particularly in the area of path planning, which is crucial for the safe and efficient navigations of unmanned vehicles. Second one, deep reinforcement learning (DRL). DRL is a cutting-edge technique that combines deep learning ability to process complex data with reinforcement learning decision-making capabilities. It has a significant potential in solving path planning issues. Improved algorithm. This presentation includes an enhanced DRL algorithm specially designed to improve path plannings in autonomous vehicles helps them navigate more efficient and avoid obstacles. Practical importance as the automotive industry shift towards the autonomous innovations like the DRL based and key to avoidance intelligent transparent system. Introduction to autonomous driving and path planning. Autonomous driving an increasingly critical field in transportation due to safety, efficiency, and convenience. Path planning. The key challenges in unmanned driving is how vehicles navigate from one point to another, especially in dynamic, unpredictable environment. Human limitation. Manually driving has inherent issues like fatigue and distraction, making autonomous system preferable. Technology potential. Autonomous driving can reduce accident, improve road safety, and reduce driver fatigue. Goal. DRL is a promising technique to improve decision making in path planning. Path planning methods. Global path planning focuses on decision a route based on a pre-mapped environment considering start and destination points. Local path planning dynamically respond to the obstacle and other vehicles adjusting routes in real-time challenges. Traditional systems struggle with the real-time adaptability, especially when obstacles and unaccepted conditions arises. Reinforcement learning. RL-based system can learn to make better navigation decision other time through the trial and error need for better methods. Existing techniques have limitation in complex or dynamical environment, promoting the need of DRL approach. Deep reinforcement learning overview. Deep learning focuses on recognizing patterns in complex data such as sensors input or visual data from the car's surroundings. Reinforcement learning enables the decision making by rewarding good actions and penalizing poor ones, allowing the system to learn over time. Deep Q network, an algorithm that helps the vehicle make decision by mapping states current situation to action next step. Role in autonomous driving. DRL helps in the vehicle learn from past experience and dynamically adapt to the different driving environment. Learning optimal paths. Through DRL, vehicles can find the best route by learning which actions result in the best reverse. Example, reaching the destination quickly with avoiding the obstacles. Proposed DRLPP algorithm multi-layer perceptron MLP, a type of neural network that enhance the DRL statements system decision making by improving data processing, improved reward functions. The DRLPP algorithm refines the reward system to give better feedback, distinction between optimal and suboptimal actions more clearly. Overfitting preventions, the new algorithm reduces overfitting, which helps it generalizing better to new unseen situation rather than believing overly tailored to trailer data. Efficient learning DRLPP is designed to make a system more efficient in terms of learning the best actions in complex environment. um, Tragedy planning by leveraging the learning process DRLPP constant optimizes from the vehicle starting point to its deserved point. Algorithm structured and components. Multi-layer perceptron processes the input data such as the sensors readings and determines the best action to take. Greedy strategies balances exploration, trying in new actions and exploration, choosing non-efficient actions early on. The algorithm explores more and as it learns the focusing on proven actions. Dual neural network system. One network predicts the current actions while the second stabilizes the learning by maintaining the consistent target values. Reward function enhances the learning by providing the more uh, nuanced reward by helping the vehicle to better distinguish between good and bad decision actions selection. The combination of this element helps the vehicle decide its next move based on the both immediate and long-term rewards. Experimental setup. TensorFlow flow platform. The experimental were carried out using the TensorFlow, a popular deep learning framework, to run the neural network model hardware. The simulations were performed on an Intel Pentium CPU and a NVIDIA GTX 3090 GPU, which is powerful enough to handle the computation demands. Simulation environment, the vehicle navigation, a grid with obstacle mimicking real world driving conditions to test how well the DRPPP algorithm can plan paths, obstacle avoidance. The simulation test how the algorithm helps the vehicle avoid the obstacles when efficient, reaching the target. Real world relevance. The controlled setup simulates the real world navigation challenges, ensuring that the algorithm translates the to practical applications. Simulation result performance comparison. DRLPP is a compared to the traditional DQN and actor critical algorithms, and it is outperformed both in the key areas. Training time. DRLPP reduces the training time required favor and iteration to find the optimal path compared to the other model. Stability. DRLPP shows more stable result with favor for fluctuation in the performance during training. Path optimization. This algorithm successfully finds the most efficient path to avoiding the obstacle more efficient than the other methods. Simulation success. The results suggest the DRLPP is high efficient for real world path planning tasks. Real world and training performance. Improved reward structure. The new reward functions in DRLPP helps the system learn the better, the clearly differentiate between the good and bad action. Faster convergence. The algorithm converges the more quickly, meaning it learns the optimal path with fewer steps and less trial and error. Reduction exploration DRLPP uh, re- reduces unnecessary exploration by quickly identifying and focusing on efficient actions. Consistency rewards as the system learns the reward matrices stabilizing shows the algorithm is learning to make a more reliable decision. Superior learning compared to the other models, DRLPP learns more efficiently, balancing exploration with exploitational to optimize the navigation. Conclusion and the future directions. Summary of the benefits. A DRLPP improves the path planning by reducing training time, feeding optimized path, and providing more stable results than traditional models. Efficiency. The algorithm requires the favor exploration step, making it faster and more efficient than existing solution. The real world potential. DRLPP has a significant applications in real world. Autonomous driving helps the vehicles navigate complex environment efficiently. In future works, the next step involved in applying DRLPP to more real world scenarios improves multi-agent system and integrating real-time data from sensors. Final truths. The DRL algorithm represent a major advancement in the autonomous path planning, offering robust solution for a future of driverless vehicles. Thank you. I hope you all understand well.